So here's something worth thinking about as you settle in tonight. The ground beneath you, wherever you are right now, is moving. Not in some poetic, metaphorical sense. It's actually physically moving. Right this second. The slab of rock you're lying on top of, whether that's a continent, an island, a coastal plain, it's drifting, creeping, grinding its way across the surface of the planet at roughly the speed your fingernails grow. A few centimeters a year. You'll never feel it. No human ever has, not directly. But give it enough time, say 100 million years or so, and that tiny motion builds mountains. And that's what we're going to talk about tonight. Mountains. The whole magnificent, violent, slow-motion story of how they're made, how they crumble, how they shape the weather and the rivers and the civilizations that grow up around them. We're going to take it slow, start from deep inside the earth, and just walk through it all together. No rush. If you drift off somewhere along the way, that's perfectly fine. Mountains are patient. They've been waiting for millions of years. They can wait a little longer. Let's start with something that seems so obvious now that it's almost hard to believe anyone ever doubted it. The continents move. They drift around the surface of the earth like enormous rafts on a very, very slow ocean. South America and Africa fit together like puzzle pieces. India used to be an island. Australia has been wandering northward for tens of millions of years. All of this is true. All of it is well-established science. And as recently as the 1960s, most geologists thought it was nonsense. The story of how we figured out that continents move is one of those beautiful, tragic tales where the person who was right got laughed out of the room and then died before anyone admitted he'd been right all along. His name was Alfred Wegener, and he was a German meteorologist, not even a geologist, which was part of the problem. Wegener was born in Berlin in 1880, studied astronomy, and then fell in love with meteorology and polar exploration. He led expeditions to Greenland, where he studied the atmosphere and ice. He was tough, curious, restless. The kind of person who would cross the Greenland ice cap on skis just to see what was on the other side. And sometime around 1910, Wegener noticed something that had been staring at mapmakers for centuries. The eastern coastline of South America and the western coastline of Africa matched, not approximately, not vaguely. They fit together with an almost eerie precision, like two pieces of a jigsaw puzzle that somebody had pulled apart. Now, other people had noticed this too. Francis Bacon commented on it back in 1620, but nobody had done anything with the observation. Wegener did. He started looking for evidence that the continents had once been joined, and he found it everywhere. Fossil evidence. There were identical fossils of a small reptile called Mesosaurus, found in both Brazil and South Africa, and nowhere else. Mesosaurus was a freshwater creature. It couldn't have swum across the Atlantic. There were matching geological formations, mountain ranges, and rock sequences that lined up perfectly when you pushed the continents back together. There were glacial deposits in tropical places like India and Africa that only made sense if those landmasses had once been near the South Pole. Wegener gathered all of this evidence and, in 1912, proposed his theory of continental drift. He published a book on it in 1915 called The Origin of Continents and Oceans, and he laid out a compelling case that all the continents had once been part of a single supercontinent. He called it Pangaea, from the Greek for all lands, and that they had since broken apart and drifted to their current positions. The reaction from the geological establishment was brutal. They didn't just disagree with Wegener, they mocked him. The president of the American Philosophical Society called his theory utter damned rot. A British geologist said it was the kind of idea you'd expect from someone who wasn't really a geologist. And here's the thing. Their objections weren't entirely unreasonable. Wegener had shown that the continents had moved, but he couldn't convincingly explain how they moved. His proposed mechanism, that the continents plowed through the ocean floor like ships through water, driven by tidal forces and the Earth's rotation, was physically implausible. Geophysicists calculated that the forces Wegener invoked were far too weak to push entire continents around. And in science, having the right answer for the wrong reason can be worse than having no answer at all. People fixate on the flawed mechanism and throw out the whole idea. Wegener died in 1930, at the age of 50, during an expedition on the Greenland ice cap. He'd been resupplying a remote weather station and was heading back to base camp when he was caught in a blizzard. His body wasn't found until the following spring. He never saw his theory vindicated, and it would take another 30 years before the evidence became so overwhelming that the geological establishment had to accept it, though by then they called it plate tectonics, not continental drift, which was a way of acknowledging that Wegener had been right about the what, while getting to be right about the how. So what is plate tectonics? Here's the picture, and it's genuinely beautiful once you see it. The Earth isn't a solid ball of rock. Think of it more like a soft-boiled egg. There's a thin, rigid outer shell, the crust, which is anywhere from 5 kilometers thick under the oceans to about 70 kilometers thick under the continents. Below the crust is the mantle, a thick layer of rock that's mostly solid but behaves, over long time scales, like an incredibly viscous fluid. Think of it like glass. Glass is technically a solid, but over centuries it can flow. The mantle is like that, but even slower. It flows over millions of years. And at the center is the core, an outer core of liquid iron, swirling and churning, generating the Earth's magnetic field, and an inner core of solid iron, compressed by unimaginable pressure, hotter than the surface of the sun. Now, the crust isn't one continuous shell. It's broken into about 15 major pieces and several smaller ones, and these pieces, these plates, are what move. They float on top of the mantle, and they're driven by convection currents in the mantle below. Here's how convection works, and you've actually seen it yourself. Think about a pot of water on a stove. The water at the bottom gets heated, becomes less dense, and rises. When it reaches the surface, it cools, becomes denser, and sinks back down. You get these circular patterns, convection cells, with hot material rising and cool material sinking. The same thing happens in the Earth's mantle, just unimaginably slowly, and on an unimaginably larger scale. Hot rock from deep in the mantle rises toward the surface. It spreads out sideways, dragging the crustal plates with it. Then it cools and sinks back down. This slow churning is what moves the plates. That's the mechanism Wegener couldn't find. And here's the thing. It's at the boundaries between these plates where all the interesting stuff happens, where the action is, where mountains are born. Because when two plates collide, when they scrape past each other, when one dives beneath another, that's where you get earthquakes, volcanoes, and mountains. The entire ring of fire around the Pacific Ocean, all those volcanoes and earthquake zones from New Zealand to Japan to Alaska to Chile, that's all plate boundaries. The Himalayas, the Andes, the Alps, the Rockies, all created by plates colliding. The Mid-Atlantic Ridge, that enormous underwater mountain range running down the middle of the Atlantic Ocean. That's where two plates are pulling apart, and new crust is being created from molten rock rising up to fill the gap. Think about that for a second. There's a mountain range in the middle of the Atlantic Ocean. It's about 16,000 kilometers long, roughly 10,000 miles, making it the longest mountain range on Earth. And most people have never heard of it, because it's almost entirely underwater. Only a few peaks poke above the surface. Iceland is one of them. Iceland is literally sitting on top of the Mid-Atlantic Ridge, straddling the boundary between the North American plate and the Eurasian plate. The island is being pulled apart, very slowly, at about 2.5 centimeters per year. There's a place in Thingvellir National Park where you can actually walk between the two plates, standing in the Rift Valley where the crust is splitting. You can reach out and touch North America with one hand and Europe with the other. It's one of the most geologically dramatic places on Earth, and it looks, honestly, like a quiet valley with some interesting rock walls. But the real mountain-building action, the stuff that creates the peaks and ranges you picture when you think of mountains, that happens where plates come together, where they collide, and the nature of the collision depends on what kind of crust is involved, because there are two fundamentally different types. Oceanic crust is thin, about 5 to 10 kilometers, and it's made of dense basaltic rock. Continental crust is thick, up to 70 kilometers in places, and it's made of lighter granitic rock. Think of oceanic crust as a thin sheet of heavy metal, and continental crust as a thick slab of lighter wood. When they meet, the physics of what happens depends on which type is meeting which. When oceanic crust meets continental crust, the denser oceanic plate slides underneath. It subducts, that's the technical term, diving down into the mantle at an angle. As it descends, it gets hotter and hotter, and the water trapped in its rocks gets squeezed out and rises into the mantle above, lowering the melting point of that mantle rock. The mantle partially melts, and that molten rock, that magma, rises up through the continental crust above, creating volcanoes. The entire western coast of South America is a textbook example of this. The Nazca Plate, an oceanic plate under the eastern Pacific, is subducting beneath the South American plate, and the result is the Andes, the longest continental mountain range on Earth, running about 7,000 kilometers along the western edge of South America, with peaks over 6,000 meters, active volcanoes, devastating earthquakes, and a geological history that stretches back over 200 million years. But the most spectacular mountain building, the process that creates the tallest, most massive ranges on Earth, happens when two plates carrying continental crust collide head-on. And the reason this is so dramatic is that continental crust is too buoyant to subduct. It's too light, it won't go down. So when two continents collide, neither one dives beneath the other. Instead, they crumple, they buckle, they fold and thrust, and pile up on each other like two cars in a head-on collision, crumpling the hood of one over the other. And the result of that crumpling is the most magnificent mountain range on Earth, the one that's been growing for about 50 million years and is still growing right now, as you lie here listening, the Himalayas. And the story of how India crashed into Asia to create them is one of the most extraordinary geological dramas in the history of this planet. Because India wasn't always where it is now, not even close. 200 million years ago, India was part of Gondwana, the great southern supercontinent, nestled up against what is now Madagascar, Antarctica, and Eastern Africa. And then, around 130 million years ago, India broke away. It separated from Gondwana and began drifting northward across what would become the Indian Ocean, moving at a speed that was, by tectonic standards, remarkably fast. About 15 centimeters per year at its peak. That's roughly 6 inches a year. Think about that. An entire subcontinent, millions of square kilometers of land, cruising across the ocean floor at the speed a child's hair grows. It doesn't sound fast, but give it 100 million years, and you've covered thousands of kilometers. And ahead of India, between it and the southern coast of Asia, there was an ocean. The Tethys Sea, geologists call it, named after the Greek goddess of the sea. For tens of millions of years, the floor of the Tethys was being subducted beneath the Asian plate as India approached, creating volcanic activity and uplifting along the southern margin of Asia. But around 50 to 55 million years ago, India arrived. The Tethys Sea closed, and the leading edge of the Indian plate collided with the Eurasian plate. Now, when I say collided, I don't want you to picture a sudden, catastrophic impact. This isn't an asteroid hitting a planet. It's two masses of continental crust, each thousands of kilometers wide, meeting at a speed of a few centimeters per year. The collision has been happening for 50 million years, and it's still going. India is still pushing into Asia right now, at about 4 to 5 centimeters per year. And the result of all that slow, relentless pressure is the Himalayas. And not just the Himalayas, but the entire Tibetan Plateau behind them, the highest and largest plateau on Earth, sometimes called the roof of the world, averaging over 4,500 meters above sea level, about the size of Western Europe. Here's what's physically happening, and it's worth taking a moment to really picture it. The collision zone is like a slow-motion car crash that's been happening for 50 million years. The sedimentary rocks that had been sitting on the floor of the Tethys Sea, limestone, shale, sandstone, all deposited over hundreds of millions of years in a warm, shallow ocean. Those rocks got caught between the two colliding continents. They were squeezed, folded, crumpled, and thrust upward. Marine sediments that had been at the bottom of the ocean were lifted kilometers into the sky. And this is why you can find seashells on the summit of Mount Everest. That's not a myth or an exaggeration. The limestone near the top of Everest is full of the fossils of marine organisms, crinoids, brachiopods, creatures that lived on the floor of the Tethys Sea perhaps 450 million years ago. The summit of the tallest mountain on Earth is made of ancient ocean floor. Think about that for a second. The highest point on the planet, 8,849 meters above sea level, is built from rocks that formed underwater. The ocean floor pushed 5.5 miles into the sky by the slow collision of two continents. And the scale of the deformation is staggering. The Indian plate hasn't just bumped into Asia. It's been driven perhaps 2,000 kilometers into the Eurasian plate. Some of that motion has been absorbed by the Indian plate sliding under the Tibetan Plateau. Some of it has been absorbed by the crust crumpling and thickening. The crust under Tibet is roughly twice the normal continental thickness, about 70 to 80 kilometers deep. And some of it has been absorbed by Asia itself being pushed sideways, squeezing eastward. China, Southeast Asia, they've been shoved aside by the force of India's collision. Major fault systems like the Altan Tag Fault and the Red River Fault are accommodating this lateral escape. It's like pushing your fist into a pile of wet sand. The sand doesn't just pile up in front of your fist, it also squeezes out to the sides. Now, if the Himalayas have been growing for 50 million years, you might wonder how tall they'd be if nothing were wearing them down. And the answer is absurdly tall. Much taller than they are now. The thing is, mountains start being destroyed the moment they start being built. Erosion, wind, rain, ice, rivers, glaciers, is constantly gnawing at them, carrying rock away grain by grain, pebble by pebble. The height of a mountain range at any given moment is a balance between the forces building it up and the forces tearing it down. The Himalayas are tall, not because they're being pushed up especially fast. They're rising at maybe a few millimeters per year, but because they're young enough that erosion hasn't had time to grind them flat. Give it another 100 million years, and the Himalayas will look like the Appalachians, ancient, rounded, worn down to gentle hills. But here's what's really clever about erosion and mountains, and this is one of those feedback loops that makes geology so elegant. When erosion removes rock from the top of a mountain, it makes the mountain lighter. And because mountains float on the denser mantle below, yes, mountains float, the same way icebergs float in water, just in rock instead of liquid. When you remove weight from the top, The mountain bobs up a little bit. It rises. This is called isostatic rebound, or isostatic adjustment, and it means that erosion doesn't just lower mountains, it also triggers them to rise back up. You grind off 1,000 meters of rock, and the mountain pops up 800 meters in response. It's like trying to push a beach ball underwater. Every time you push it down, it bounces back up. This feedback means mountains can persist much longer than they would if erosion were simply carving them down from a fixed height. They're in a constant, dynamic balance, being pushed up from below, carved down from above, and bouncing back in between. This is why Mount Everest is still growing. Not by a lot. GPS measurements show the summit rising at about 4 millimeters per year, roughly the thickness of a nickel. But it's measurably rising, even after 50 million years, because India is still pushing, and the isostatic adjustments are still happening. And it's not just Everest. The entire Himalayan front is active. Nepal sits right on the collision zone, which is why it's so seismically dangerous. The devastating earthquake that struck Nepal in April 2015, the Gorkha earthquake, magnitude 7.8, that was a direct consequence of the Indian plate lurching a few meters northward beneath the Eurasian plate. The earthquake killed nearly 9,000 people and triggered avalanches on Everest that killed more climbers than any single event in the mountain's history. The geological process that builds the world's tallest mountains is the same process that destroys the cities at their feet. And this brings up something important, something about timescales that's worth sitting with. When you look at a mountain, it looks permanent. It looks like the most solid, unchanging thing you could possibly imagine. And on a human timescale, it basically is. The mountains you see today are the same mountains your great-great-great-grandparents saw. But on a geological timescale, the scale the Earth operates on, mountains are temporary. They're events. They rise, they erode, they vanish. The Appalachian Mountains in eastern North America were once as tall as the Himalayas, maybe taller. They formed about 480 million years ago, long before the current Himalayas existed, when ancient continents collided in an event called the Taconic Orogeny, followed by the Akkadian and Alleghanian orogenies. The Appalachians were once enormous, sharp-peaked, towering. And now they're gentle, rounded hills. The tallest peak, Mount Mitchell in North Carolina, reaching only 2,037 meters. 480 million years of erosion turned a Himalayan-scale range into something you can hike in an afternoon. That's what time does to mountains. But not all mountains are built by continental collisions. Not all of them are the result of two tectonic plates crumpling into each other. There are other ways the Earth builds tall things, and they're completely different in their mechanics, their timescales, and the kinds of landscapes they create. And one of the most dramatic of those other methods involves something far more violent than the slow grinding of plates. It involves the Earth opening up and spilling its insides out onto the surface. It involves volcanoes. And the mountains that volcanoes build are among the most beautiful, most dangerous, and most geologically fascinating things on the planet. Think about Mount Fuji for a second. That iconic, almost perfect cone shape, rising symmetrically above the Japanese landscape. Or Mount Kilimanjaro, standing alone on the East African plain, snow-capped and enormous. Or Mount Rainier, looming over Seattle like a silent giant. These are volcanic mountains, and they're built in a fundamentally different way from fold mountains like the Himalayas. They're not pushed up from the sides by colliding plates. They're built from the inside, layer by layer, eruption by eruption, as molten rock from deep in the earth rises to the surface and piles up. The mechanism is actually quite elegant. Remember subduction zones, where one plate dives beneath another? As the descending plate sinks into the mantle, it releases water into the overlying mantle rock, lowering its melting point. Pockets of magma form, less dense than the surrounding solid rock, and they rise, slowly at first, pooling in magma chambers kilometers below the surface. And then, when the pressure builds enough, the magma forces its way to the surface through fractures and conduits in the rock above, and you get an eruption. Lava flows out, ash and rock fragments are blasted into the air, and over time, thousands of eruptions over tens or hundreds of thousands of years, a mountain is built. And the shape of that mountain depends on the chemistry of the magma. This is one of those details that seems technical at first, but turns out to be the difference between a gentle, flowing eruption you can watch from a safe distance and a catastrophic explosion that can kill tens of thousands of people. Magma with low silica content, basaltic magma, is runny, fluid, easy-flowing. Think of it like honey. When this kind of magma erupts, it flows smoothly down the sides of the volcano in rivers of lava. The resulting mountain has gentle slopes, a broad base, and a wide, shallow profile. These are called shield volcanoes, and the best examples are in Hawaii. Mauna Loa and Mauna Kea are shield volcanoes, and they're enormous. Mauna Kea, if you measure from its base on the ocean floor, is actually taller than Everest, over 10,000 meters from base to summit. It's just that most of it is underwater. The eruptions that build shield volcanoes are spectacular to watch, but relatively safe. You can often see them coming, and the lava moves slowly enough that you can walk away from it. But magma with high silica content, andesitic or rhyolitic magma, that's a different story entirely. High silica magma is thick, viscous, sticky. It's more like cold tar than honey. And because it's so viscous, gases dissolved in the magma can't escape easily. They build up pressure, like shaking a bottle of soda. And when the pressure finally exceeds the strength of the rock above, the result isn't a gentle flow, it's an explosion. A violent, devastating, landscape-altering explosion. These eruptions produce stratovolcanoes, also called composite volcanoes, mountains with steep sides, built from alternating layers of lava, ash, and volcanic debris. Mount Fuji is a stratovolcano. Mount Vesuvius is a stratovolcano. Mount St. Helens is a stratovolcano. And the history of stratovolcanoes is punctuated by some of the most destructive natural disasters in recorded history. And one of the most instructive, one of the ones that really shows you what these mountains are capable of, happened not in some distant past, but in 1980, in the state of Washington, in the northwest corner of the United States. Mount St. Helens. Before May 18, 1980, Mount St. Helens was a beautiful, symmetrical peak in the Cascade Range, sometimes called the Mount Fuji of America. It stood 2,950 meters tall, covered in glaciers and old-growth forest. People hiked on it, camped near it, fished in the lakes at its base. It was the kind of mountain that ended up on postcards. And then, over the course of about 2 months, it destroyed itself. The warning signs started in March 1980. Small earthquakes, hundreds of them, centered beneath the mountain, steam venting from the summit crater, and then a bulge appeared on the north face, a massive swelling in the mountainside, growing outward at a rate of about 1.5 meters per day. Magma was pushing up inside the mountain, inflating it like a balloon. Geologists knew something was coming. The question was how big. The answer came on the morning of May 18th. At 8:32 a.m. local time, a magnitude 5.1 earthquake struck directly beneath the mountain. The north face, that enormous bulge, collapsed. It was the largest landslide in recorded history. Roughly 2.8 cubic kilometers of rock, ice, and soil, an entire mountainside, sliding down and outward at speeds up to 250 kilometers per hour. And the collapse uncorked the pressurized magma system inside the mountain like popping a champagne bottle. A lateral blast, not upward but sideways, exploded out of the north face at supersonic speed. The blast cloud, superheated gas, and pulverized rock reached temperatures of around 300 degrees Celsius and traveled at over 1,000 kilometers per hour. It flattened old-growth forest like matchsticks over an area of nearly 600 square kilometers. Trees that had stood for centuries were snapped off at the base and laid flat in neat rows, pointing away from the mountain, like blades of grass blown down by a giant exhaling. 57 people died. Most of them were outside the exclusion zone that had been set up around the mountain. Hikers, loggers, a few residents who had refused to evacuate. The most famous victim was Harry Truman, no relation to the president, an 83-year-old innkeeper who lived at the base of the mountain at Spirit Lake Lodge and refused to leave. He said the mountain was his home, and he'd rather die than abandon it. He got his wish. His lodge and Harry Truman himself were buried under 50 meters of volcanic debris. His body was never found. But here's the engineering lesson buried in the tragedy. The eruption of Mount St. Helens wasn't unexpected. Geologists had been monitoring the mountain for months. They had identified the bulge, measured its growth rate, and warned that a major eruption was likely. The exclusion zone they established saved thousands of lives. The failure wasn't scientific. It was institutional and human. The exclusion zone wasn't large enough, and it was compromised by political pressure. Logging companies wanted to keep their operations running. Local residents resisted evacuation. The governor negotiated special access permits. And some people simply didn't believe that a mountain they'd known their entire lives could actually explode. The geology was predictable. The human response was where things broke down. The eruption reduced the height of the mountain from 2,950 meters to 2,549 meters. It blew 400 meters off the top. The beautiful, symmetrical cone was replaced by a horseshoe-shaped crater, open to the north. And here's what's fascinating about what happened next. Almost immediately, life started coming back. Within weeks, plants were poking through the ash. Within a few years, wildflowers were blooming. Frogs and insects returned. The ecological recovery of the Mount St. Helens blast zone has been one of the most intensively studied natural recolonization events in history, and it's taught ecologists enormous amounts about how ecosystems rebuild after catastrophic disturbance. The mountain that destroyed everything around it also created a natural laboratory for understanding life's resilience. Now, stratovolcanoes like St. Helens are dramatic, but they're not the only way volcanoes build mountains, and they're not even the most volumetrically impressive. For that, you need to look at a different kind of volcanic activity altogether, the kind that builds not a single peak, but an entire elevated landscape. And this brings us to something called large igneous provinces, which is one of those terms that sounds dry until you understand what it actually means. It means unimaginably vast volumes of lava flooding across the surface of the Earth, covering millions of square kilometers, in events so massive they've been linked to some of the worst mass extinctions in the planet's history. The Deccan Traps in western India are a good example. Around 66 million years ago, yes, right around the time the dinosaurs went extinct, enormous volcanic eruptions poured basaltic lava across what is now India, covering an area of about 500,000 square kilometers in some estimates, with lava piles reaching up to 2,000 meters thick in places. The word traps comes from the Swedish word for stairs, because the basalt layers erode into step-like formations. Whether the Deccan volcanism contributed to the dinosaur extinction, alongside or perhaps in combination with the Chicxulub asteroid impact, is still debated, but the scale of the eruptions is beyond anything in recent human experience. We're talking about enough lava to bury the entire state of Texas under a kilometer of rock. That's not a mountain in the traditional sense, but it creates elevated terrain, plateaus, highlands that shape the landscape for hundreds of millions of years. Now, it's worth pausing here to talk about something that connects volcanic mountains to a completely different kind of geological wonder, because there's a type of volcanic mountain building that doesn't happen at plate boundaries at all. It happens right in the middle of a plate, far from any subduction zone or rift, and it's caused by what geologists call a mantle plume, a column of exceptionally hot rock rising from deep in the mantle, possibly from as deep as the boundary between the mantle and the outer core, nearly 3,000 kilometers below the surface. Think of it like a lava lamp. You know how in a lava lamp, blobs of wax heat up at the bottom, become less dense, and rise slowly through the surrounding fluid? A mantle plume is like that, but scaled up to planetary dimensions. A plume of abnormally hot mantle material rises through the surrounding mantle, reaches the base of the crust, and creates a volcanic hotspot. The Hawaiian Islands are the most famous example. Hawaii sits in the middle of the Pacific Plate, thousands of kilometers from the nearest plate boundary. There's no subduction happening, no rift opening. Instead, there's a mantle plume beneath the Pacific Plate, pumping heat and magma upward. And because the Pacific Plate is moving northwestward over this stationary plume, the hotspot has burned a chain of volcanic islands across the ocean floor, like a welding torch tracing a line as the metal sheet slides over it. The Big Island of Hawaii, with its active volcanoes Kilauea and Mauna Loa, is currently sitting over the hotspot. The older islands to the northwest, Maui, Molokai, Oahu, Kauai, were each built over the hotspot and then carried away by plate motion, gradually eroding and sinking as they moved. If you follow the chain far enough to the northwest, past the visible islands, you find the Emperor Seamount chain, submerged, eroded remnants of ancient Hawaiian volcanoes, stretching all the way to the Aleutian Trench near Alaska. The oldest seamounts in the chain are about 80 million years old. That's 80 million years of volcanic activity from a single hotspot and counting. And the Yellowstone volcanic system in the western United States is another hotspot example, though a much more terrifying one. Yellowstone sits over a mantle plume that's been active for at least 17 million years. As the North American plate has drifted southwestward over the plume, it's left a track of volcanic calderas and lava flows stretching from northeastern Oregon to its current position in Wyoming. And the current Yellowstone caldera, the one beneath Yellowstone National Park, the one that powers the geysers and hot springs that tourists flock to see, is the scar of an eruption about 640,000 years ago that was roughly 1,000 times more powerful than the Mount St. Helens eruption. It ejected over 1,000 cubic kilometers of material. That's a volume hard to even conceptualize. The ash covered much of North America, and Yellowstone will erupt again. The geological record is clear about that. When exactly, nobody knows. The current volcanic system shows no signs of an imminent eruption, and eruptions of this magnitude typically happen hundreds of thousands of years apart. But the fact that something that powerful is sitting beneath a national park, quietly heating the groundwater and occasionally rattling the seismographs, is a useful reminder that the Earth's interior doesn't care about our schedules or our comfort. But let's shift from volcanic mountains to a third way that mountains can form, one that's less dramatic than either tectonic collision or volcanic eruption, but produces some of the most striking mountain landscapes in the world: fault block mountains. And to understand these, you need to understand what happens when the Earth's crust is being pulled apart rather than pushed together. Think about it this way. When tectonic plates converge, the crust compresses, crumples, and thickens. That's what makes the Himalayas. But when plates diverge, when they move apart, the crust stretches and thins. And when rock is stretched, it doesn't stretch smoothly, like taffy. It's brittle, it cracks, it breaks along faults, fractures in the rock where one side slides relative to the other. And when the crust breaks into blocks along these faults, some blocks tilt upward and others drop downward. The upthrown blocks become mountains, the downthrown blocks become valleys. This is how fault block mountains form, and the result is a distinctive landscape of steep-sided ridges separated by flat-bottomed valleys. The Basin and Range Province of the western United States is the textbook example. If you've ever driven across Nevada, you know the landscape. Long, parallel mountain ranges separated by broad, flat valleys, repeating like waves, range after range stretching to the horizon. This entire region, covering a vast area from eastern California to central Utah, is being stretched apart by tectonic forces. The crust has broken into hundreds of fault blocks, some tilted up to form mountain ranges, others dropped down to form basins. The Grand Tetons in Wyoming are another beautiful example of fault block mountains. The eastern face of the Tetons is a steep fault scarp, rising dramatically from the flat valley of Jackson Hole, while the western slope is a more gradual incline. The contrast is striking. You can be standing in a flat valley and looking straight up at a nearly vertical wall of rock towering 2,000 meters above you. And then there's a fourth type of mountain that doesn't fit neatly into any of these categories: dome mountains. These form when magma pushes up from below but never actually breaks through to the surface. Instead, it bows the overlying rock upward, creating a dome-shaped bulge. The Black Hills of South Dakota are a classic example, an elongated dome of uplifted rock, with the oldest rocks exposed at the center, where erosion has stripped away the overlying layers. Mount Rushmore, incidentally, is carved into the granite core of this dome. The granite that the four presidents' faces are carved into is about 1.7 billion years old. Precambrian rock that was once deep in the Earth's crust and was pushed up to the surface by the doming process, then exposed by erosion. So now you've got the basic toolkit. Mountains can be made by plates colliding and crumpling the crust. Fold mountains. They can be built up by volcanic eruptions. Volcanic mountains. They can be created when the crust stretches and breaks into tilted blocks. Fault block mountains. And they can form when magma pushes up the overlying rock without breaking through. Dome mountains. And in the real world, most mountain ranges involve some combination of these processes. The Rockies, for instance, are complicated. They involve ancient fold and thrust events, volcanic activity, fault block structures, and uplift that's still not fully understood. The Alps involve subduction, continental collision, and complex folding. Mountains rarely come from a single neat process. The Earth is messier than the textbooks, but regardless of how a mountain is made, the moment it exists, it starts being unmade. Erosion begins immediately, and the forces of erosion are patient, relentless, and surprisingly powerful. A raindrop doesn't seem like it could do anything to granite, but 1 trillion raindrops over 1 million years can carve a canyon. And that slow, patient destruction is what gives mountains their shape, the shape you actually see when you look at them. Because the raw form of a mountain, the form that tectonic or volcanic forces create, is just the starting point. Everything beautiful and dramatic about mountain landscapes, the sharp ridges, the U-shaped valleys, the cirques and arêtes and hanging waterfalls, all of that is carved by erosion. The sculptor, in a very real sense, is water. Water and ice and time. And the way they work together to shape mountains is one of the most elegant stories in all of geology. So let's spend some time with it, because this is where mountains go from being impressive piles of rock to being genuinely, breathtakingly beautiful. Start with water. Plain, liquid water. It seems harmless, right? But water is, chemically and physically, one of the most destructive substances on Earth when it comes to rock. And it works in several ways simultaneously. First, there's the simple mechanical force of flowing water. A river doesn't just flow over rock. It carries sediment with it, sand and gravel and pebbles, and those particles act like sandpaper, grinding away at the riverbed and the canyon walls. Over millions of years, this abrasion can carve enormous valleys. The Grand Canyon, which isn't technically a mountain, but it's a mountain landscape turned inside out, if you think about it, was carved primarily by the Colorado River over the last 5 to 6 million years, cutting through over a kilometer of rock. A river and time, that's all it took. But water doesn't just erode mechanically. It erodes chemically too. Rainwater absorbs carbon dioxide from the atmosphere, forming a weak carbonic acid. This slightly acidic water dissolves certain types of rock, particularly limestone and marble, eating away at them molecule by molecule. This chemical weathering is why limestone landscapes develop caves, sinkholes, and karst topography. Those dramatic landscapes of towers and pinnacles and disappearing rivers that you find in places like southern China, Slovenia, and the Kentucky hills. In mountain environments, chemical weathering works alongside mechanical erosion, weakening the rock so that physical forces can break it apart more easily. And then, there's the most elegant destroyer of all, freeze-thaw weathering. This is beautifully simple. Water seeps into cracks in the rock. The temperature drops below freezing. The water turns to ice. And when water freezes, it expands by about 9%. That expansion exerts enormous pressure on the walls of the crack, widening it. Then the temperature rises, the ice melts, the water seeps deeper into the now wider crack. The cycle repeats, day after day, winter after winter, for thousands of years. And gradually, the crack grows, the rock weakens, and eventually, a chunk breaks free and tumbles down the mountainside. This process, frost wedging, is one of the primary forces shaping mountain landscapes above the tree line. Those fields of broken rock you see on high mountain slopes, they're called talus fields or scree slopes. They're the product of freeze-thaw cycles patiently dismantling the mountain, one fragment at a time. But the most powerful sculptor of mountain landscapes isn't liquid water or freezing water. It's glaciers, rivers of ice, flowing under their own weight, grinding and carving the rock beneath them with a force and precision that nothing else on Earth can match. And the landscapes that glaciers create are among the most spectacular on the planet. Here's how a glacier works. In high mountains, where more snow falls each winter than melts each summer, the snow accumulates year after year. The weight of the overlying snow compresses the snow beneath it, gradually transforming it from fluffy snowflakes to dense, crystalline ice. Over decades and centuries, this ice builds up into a mass thick enough, usually at least about 30 meters, that it starts to flow under its own weight, creeping downhill through a valley. It moves slowly, maybe a few centimeters a day in some cases, though some glaciers can surge at speeds of several meters per day. And as it moves, it does extraordinary things to the rock beneath it. The bottom of a glacier is a grinding machine. The ice freezes onto the bedrock beneath it, and as the glacier moves forward, it plucks chunks of rock from the bed and drags them along. These rocks, embedded in the base of the ice, act like the teeth of a giant file, scraping and scratching the bedrock as the glacier slides over it. This process, glacial abrasion, can polish rock to a mirror shine or carve deep parallel grooves, called striations. You can find glacially polished rock in mountain ranges all over the world, smooth surfaces covered in fine parallel scratches that tell you exactly which direction the glacier was flowing, like giant claw marks across the landscape. And the shapes that glaciers carve are distinctive and dramatic. A river valley is typically V-shaped, narrow at the bottom, widening gradually toward the top, carved by water cutting down into the rock. But a glacial valley is U-shaped, broad, flat-bottomed, with steep, nearly vertical walls. That's because a glacier fills the entire valley, grinding not just the bottom but the sides as well, widening and deepening the valley into that characteristic U profile. Yosemite Valley in California is one of the most famous glacially carved valleys in the world. Its flat floor, its sheer granite walls, El Capitan rising nearly 1,000 meters straight up from the valley floor, Half Dome with its famous curved face, all of that was sculpted by glaciers during the ice ages. Then there are cirques, bowl-shaped depressions carved into the mountainside at the head of a glacier, where the ice accumulates and begins its downhill journey. Cirques often contain small lakes after the glacier melts, called tarns. When cirques on opposite sides of a mountain erode back into the ridge, they can create a narrow, knife-edge ridge called an arête. And when 3 or more cirques erode into a peak from different sides, they create a horn, a steep, pyramidal summit with sharp edges. The Matterhorn, on the border of Switzerland and Italy, is the most famous example. That iconic, almost impossibly pointed shape, that's what happens when glaciers carve into a mountain from multiple directions simultaneously. It's erosion as sculpture. The raw mountain, pushed up by tectonic forces millions of years ago, was a rounded mass of rock. The glaciers came along and carved it into something magnificent. Here's something else that's worth pausing on, because it connects the erosion story to the tectonic story in a way that's surprisingly intimate. Remember isostasy, the idea that mountains float on the mantle, and that when you remove weight from the top, the mountain bobs up? Well, glaciers are incredibly effective at removing weight. During ice ages, enormous glaciers sit on top of mountain ranges, grinding them down, carrying away billions of tons of rock. But at the same time, the weight of the ice itself pushes the crust down. So the mountain is being simultaneously carved by the glacier and pushed down by its weight. And then the ice age ends. The glaciers melt, and 2 things happen at once. The erosive force is removed, and the weight is removed. The mountain bounces back up. This post-glacial rebound can be surprisingly fast in geological terms. Scandinavia is still rebounding from the ice sheets that covered it during the last ice age, which ended about 10,000 years ago. Parts of Sweden and Finland are rising at about a centimeter per year, which is fast enough that it's measurable on human timescales and actually creates practical problems. Harbors that were deep enough for Viking ships are now too shallow for modern boats. The land is literally rising out of the sea. And this interplay between building and destroying, between the tectonic forces that push mountains up and the erosive forces that carve them down, this interplay is what gives the Earth's surface its incredible variety. Young mountain ranges like the Himalayas and the Andes are tall, sharp, rugged, with steep slopes and deep valleys. They're still growing faster than erosion can wear them down. Old mountain ranges like the Appalachians and the Scottish Highlands are low, rounded, gentle. Erosion has had hundreds of millions of years to smooth them out, and the tectonic forces that built them are long gone. And in between, you get everything. The Alps, the Rockies, the Atlas Mountains of North Africa, ranges at various stages of the cycle, each with its own character, its own personality, shaped by the specific combination of forces that built it and the specific agents that have been eroding it. But mountains don't just sit there being shaped by wind and water and ice. They reach up into the atmosphere, and they change the weather itself. They force air masses to rise. They create rain on one side and desert on the other. They generate their own winds and storms and microclimates. And the way they do this, the way a pile of rock can alter the behavior of the atmosphere, is one of the most beautiful examples of how the solid Earth and the fluid atmosphere interact. It's called the orographic effect, and it's responsible for some of the wettest and some of the driest places on the planet being right next to each other, separated by nothing more than a ridge of rock. Here's how it works, and once you understand this, you'll see it everywhere. Imagine a mass of moist air, let's say air that's picked up water vapor as it traveled across the ocean, moving inland. It's flowing along at whatever altitude, carrying its moisture with it. And then it hits a mountain range. The air can't go through the mountain, so it has to go over it. And as air rises, it cools. This is a fundamental fact about the atmosphere. Air pressure decreases with altitude, so rising air expands, and expanding air cools. The cooling rate is about 6.5 degrees Celsius per 1,000 meters for moist air, a bit more for dry air. And as the air cools, its ability to hold moisture decreases. At some point, the air cools enough that its moisture starts condensing out as clouds. Keep rising, and the moisture falls as rain or snow. So the windward side of the mountain, the side facing the incoming moist air, gets drenched. Heavy rainfall, lush forests, sometimes among the wettest places on Earth. And then the air crests the mountain and starts descending on the other side. Now the process reverses. As the air descends, it compresses. As it compresses, it warms. And warm air can hold more moisture, so it stops raining. The air arrives on the leeward side of the mountain, warm, dry, and thirsty. This is called a rain shadow, and it creates some of the starkest environmental contrasts on the planet. The western slopes of the Cascade Range in Washington state receive over 250 centimeters of rain per year. Dense, lush, temperate rainforest. Drive 30 miles east, over the mountains, and you're in semi-arid grassland, receiving less than 25 centimeters. Same latitude, same distance from the ocean, completely different world. The Atacama Desert in Chile, one of the driest places on Earth. Some weather stations there have never recorded measurable rainfall, sits in the rain shadow of the Andes. The Gobi Desert exists partly because the Himalayas and the Tibetan Plateau block moist air from the Indian Ocean. The mountains aren't just passive landscape features. They're active participants in the Earth's climate system, redirecting moisture, creating deserts, nurturing forests, and the effects go far beyond just local rainfall. Mountains can influence weather patterns on a continental and even global scale. The Tibetan Plateau, that enormous elevated landmass created by the India-Asia collision, is sometimes called the third pole because of its vast stores of ice, but it's also a giant atmospheric heat engine. In summer, the plateau heats up, creating a massive area of low pressure that draws in moist air from the Indian Ocean. This is the primary driver of the South Asian monsoon, the seasonal rainfall pattern that over 1 billion people depend on for their agriculture and drinking water. Without the Himalayas and the Tibetan Plateau, the monsoon would be dramatically different, and the entire climate of South and Southeast Asia would be transformed. Think about that. A geological event that began 50 million years ago, 2 continents colliding, created a mountain range that today controls the rainfall patterns that feed a substantial fraction of humanity. The rocks shape the weather, and the weather shapes civilizations. It's all connected, but the atmosphere is only part of the story. Mountains also shape the flow of water across the surface of the Earth, And in doing so, they shape where people live, where cities grow, where borders are drawn. Because mountains are where rivers are born. Think about it. Rain and snow fall disproportionately on mountains, thanks to the orographic effect we just talked about. And all that water has to go somewhere. It flows downhill, gathering in streams, joining other streams, becoming rivers, and eventually reaching the ocean or an inland lake or basin. Mountains are the source of most of the world's major rivers. The Ganges, the Indus, the Brahmaputra, they're all born in the Himalayas. The Colorado River starts in the Rocky Mountains. The Rhine begins in the Swiss Alps. The Nile, the longest river on Earth, has its sources in the mountains of East Africa. Without mountains, the world's river systems would be utterly different, and with them, the patterns of human settlement, agriculture, and civilization. And this brings us to something I find genuinely fascinating: the way mountains have shaped human history, not just as obstacles to be crossed, but as strategic barriers, cultural dividers, sources of resources, and objects of reverence. Because mountains aren't just geological features, they're human stories. Consider this: the Alps have been one of the most important geographical features in European history. They form a natural barrier between the Mediterranean world and northern Europe, and for millennia, they've shaped the movement of armies, traders, and ideas. When Hannibal crossed the Alps with his elephants in 218 BCE, and we still argue about exactly which pass he used, it was considered one of the great military feats of the ancient world, precisely because the mountains were supposed to be impassable. The Romans built roads over alpine passes that are still in use today. The Gotthard Pass, connecting northern and southern Switzerland, has been a crucial trade route since at least the 13th century. The importance of controlling these mountain passages has shaped Swiss politics and identity for centuries. Switzerland's famous neutrality and its decentralized political structure are partly products of its mountainous geography, which made the country difficult to invade and encouraged independent valley communities. And the engineering challenges of crossing mountains have driven some of humanity's most ambitious construction projects. Let's talk about tunnels for a second, because there's something almost heroic about the idea of boring through a mountain, taking the most solid, immovable thing in the landscape and putting a hole right through it. The Gotthard Base Tunnel, completed in 2016, is the longest and deepest traffic tunnel in the world. It runs 57.1 kilometers through the Swiss Alps, connecting the towns of Erstfeld in the north to Bodio in the south. The tunnel passes through rock as deep as 2,300 meters below the surface, nearly 1.5 miles of solid mountain above your head. It took 17 years to build, involved the excavation of roughly 28 million tons of rock, and cost about 12 billion Swiss francs. Think about what that means in practical terms. You're boring a hole through the heart of the Alps, through rock that's been there for hundreds of millions of years, dealing with pressures that increase with depth, temperatures that climb as you go deeper. The rock at the deepest point of the tunnel is naturally around 46 degrees Celsius, and water. Water is the nemesis of tunnel builders. You're cutting through rock that may contain aquifers, underground rivers, pockets of pressurized water that can flood a tunnel section in minutes. During the construction of the Gotthard Base Tunnel, workers encountered water inflows of up to 600 liters per second in some sections. That's 600 liters of water pouring into your tunnel every second. The engineering required to manage that, to keep boring forward through it, to seal it and drain it, and keep the tunnel dry and stable, that's extraordinary. And the reason they built it is beautifully practical. The old rail route over the Gotthard Pass involved steep grades, sharp curves, and a summit altitude of about 1,150 meters. Trains had to climb laboriously over the mountain using long spiral tunnels to gain altitude. The base tunnel eliminates all of that. It runs nearly flat, at an elevation of around 500 meters, so trains can pass through at up to 250 kilometers per hour, cutting the transit time from Zurich to Milan from about 3.5 hours to about 2 hours and 40 minutes. That might not sound dramatic, but in terms of freight capacity, it's transformative. Flat routes mean heavier trains, which means more goods can be moved by rail instead of by truck, which means less diesel exhaust, less highway congestion, less carbon. The engineering serves the economics, and the economics serve the environment. It's a beautiful chain. But not all mountain engineering goes smoothly. Mountains are inherently dangerous places to build, and the history of mountain construction is littered with disasters, some of them catastrophic. And often, the failures come from underestimating the mountain, from not fully understanding the geology, or from pushing too hard, too fast, with insufficient caution. One of the most instructive examples is the Vajont Dam disaster of 1963 in the Italian Alps. This is a story that every civil engineer should know, because it's a perfect, terrible case study in what happens when engineering ambition outpaces geological understanding. The Vajont Dam itself was an engineering triumph. Completed in 1961, it was a double curvature arch dam, 261 meters tall. At the time, one of the tallest dams in the world. It was built in a narrow gorge of the Vajont River, a tributary of the Piave, in the Dolomite Alps of northeastern Italy. The engineering of the dam was flawless. The concrete was sound, the design was elegant, the structure was strong. The dam, in fact, survived the disaster that followed, essentially intact. It's still standing today. The problem wasn't the dam. The problem was the mountain. The slopes above the reservoir, particularly the southern slope of Monte Toc, were made of layered limestone and clay, and there had been signs of instability from the beginning. During the initial filling of the reservoir in 1960, a section of the slope had shifted, a landslide of about 700,000 cubic meters. The operators partially drained the reservoir, the slope stabilized, and they began refilling. Over the next few years, monitoring showed that the slope was continuing to creep, moving a few centimeters per day. Animals on the farms above the reservoir were becoming agitated. Cracks were appearing in the ground. Geologists warned that a major landslide was possible, but the operators continued filling the reservoir, believing they could manage the situation by carefully controlling the water level. On October 9, 1963, at about 10:39 p.m., the southern slope of Monte Toc collapsed. Not a small landslide. An enormous, catastrophic failure. Roughly 260 million cubic meters of rock. An entire mountainside, a mass about 1 kilometer wide and nearly 2 kilometers long, moving as a single coherent block, slid into the reservoir at speeds estimated at up to 110 kilometers per hour. The landslide displaced the water in the reservoir, and a wall of water, estimated at about 250 meters high, overtopped the dam. 2 waves of water, one upstream, one downstream, devastated the surrounding area. The downstream wave, channeled through the narrow Vajont Gorge, struck the town of Longarone and several nearby villages with devastating force. The town was essentially erased. Nearly 2,000 people were killed. Entire communities were obliterated in minutes. And the dam itself? The dam survived. It took the impact of the wave, the impact of millions of tons of water overtopping it by 100 meters, and it held. That's how well it was engineered. The failure wasn't in the dam. The failure was in the decision to build a reservoir against an unstable mountain slope, and in the failure to take the warning signs seriously enough, quickly enough. The geology was telling them something, and the institutional response was too slow, too optimistic, too wedded to the project's continuation. There's a broader lesson there about engineering in mountain environments. The mountain always gets a vote. You can build the most elegant structure in the world, but if you don't understand the ground it's sitting on, the mountain will humble you. And this isn't just a historical concern. Mountain hazards remain some of the most dangerous and unpredictable natural risks on Earth. Landslides, avalanches, glacial lake outburst floods. These are ongoing threats in mountainous regions worldwide. A glacial lake outburst flood, or GLOF, happens when a lake that's formed behind a moraine dam, a pile of rocky debris left behind by a retreating glacier, suddenly breaks through its dam and sends a massive flood of water and debris down the valley. These events can be catastrophic. In 1941, a GLOF in Peru's Cordillera Blanca range destroyed 1/3 of the city of Huaraz and killed an estimated 5,000 people. As climate change accelerates glacier retreat, more and more of these unstable glacial lakes are forming, and the risk of GLOFs is increasing. It's a direct connection between global warming, mountain glaciology, and human safety in mountain valleys. Let me give you one more example of mountain engineering, because it's a story that shows the other side. What happens when you get it right? When the engineering and the geology work together instead of against each other. The Millau Viaduct in southern France. Completed in 2004, it's the tallest bridge in the world. Its tallest pillar, Pier P2, stands 343 meters, taller than the Eiffel Tower. The bridge carries the A75 autoroute across the valley of the River Tarn, near the town of Millau, in a region where the Massif Central meets the limestone plateaus called the Causses. The valley is about 2.5 kilometers wide and over 270 meters deep, and before the bridge was built, traffic had to descend into the valley on narrow, winding roads, crawl through the town of Millau, and then climb back out the other side. Summer traffic jams could last for hours. The solution was to fly across the valley on a cable-stayed bridge that barely touches the ground. The bridge has 7 slender piers, each one a marvel of structural engineering, tapering gently as they rise from the valley floor. The deck itself is 2,460 meters long and sits at an altitude of about 270 meters above the river. Driving across it in clear weather is like flying. You look down at clouds forming below you in the valley, while the plateaus stretch away on either side. The design, by the structural engineer Michel Virloju and the architect Norman Foster, had to contend with the geology of the valley floor and the limestone plateaus, the variable wind loads at that altitude, the thermal expansion of a deck nearly 2.5 kilometers long, and the need to build the piers on ground that included both solid limestone and softer, less stable layers. Each pier foundation was custom designed based on the specific geology at its location. Some required drilling through 50 meters of unstable ground to reach solid rock, and the construction process itself was remarkable. The deck was not built in place, it was too high, and the valley too wide for conventional scaffolding. Instead, the deck was assembled on the plateaus at each end and slid out over the valley on temporary pylons, hydraulically pushed forward a few meters at a time. Think about that, a steel deck weighing 36,000 tons, being pushed sideways across a void nearly 300 meters deep. The engineering precision required to keep that deck aligned, level, and stable during the launch was extraordinary. The Millau Viaduct has been in service for over 20 years now, carrying millions of vehicles per year. It's become a landmark, a tourist attraction in its own right, and a symbol of what's possible when engineers work with the mountain landscape rather than against it. The bridge doesn't conquer the valley. It floats across it. It treats the geology with respect, placing its foundations carefully, spanning the gap with elegance rather than brute force. It's a different philosophy from blasting a tunnel through a mountain, and both approaches have their place. But let's shift from the dangers of mountains to something quieter and more fundamental. Let's talk about what mountains are actually made of. Not just in the abstract, not just rock, but what kinds of rock, and how those rocks tell the story of a mountain's history. Because every mountain is a library. Every cliff face, every exposed layer, every boulder field is a page in a story that stretches back millions or billions of years. And if you know how to read it, the story is astonishing. There are 3 fundamental types of rock, and you've probably heard their names: igneous, sedimentary, and metamorphic. But understanding what those categories actually mean and how they relate to each other tells you almost everything about how mountains are built, deformed, and worn away. Igneous rock is rock that formed from molten material. The word comes from the Latin ignis, meaning fire. When magma cools and solidifies, either underground or on the surface, you get igneous rock. If it cools slowly, deep underground, the minerals have time to grow into large, visible crystals, and you get coarse-grained rock like granite. If it cools quickly, on the surface, think lava flows, the crystals are tiny, and you get fine-grained rock like basalt. Granite is the backbone of most continental mountain ranges: the Sierra Nevada in California, the core of the Rockies, the Great Batholiths of the Canadian Coast Mountains, all granite or granite-like rock, formed from magma that cooled deep in the crust and was later exposed by uplift and erosion. When you look at the sheer granite faces of Yosemite, El Capitan, Half Dome, you're looking at rock that crystallized from molten magma perhaps 100 million years ago, deep underground, and has been slowly revealed as the overlying rock was stripped away. Sedimentary rock is completely different. It's made from the fragments of other rocks, sand, mud, pebbles, shells, that have been deposited in layers, usually by water or wind, and then compressed and cemented over time into solid rock. Sandstone, limestone, shale, these are all sedimentary. And here's the beautiful thing about sedimentary rock. Because it's deposited in layers, it records time. Each layer represents a period of deposition, a particular environment, a particular era. The bottom layers are older, the top layers are younger. This principle, called the law of superposition, was articulated by the Danish scientist Nicolas Steno back in 1669, and it's one of the foundations of geology. When you see a cliff of layered sedimentary rock in a mountain, you're looking at a timeline written in stone. Each band of color, each change in texture, represents a change in conditions. A shallow sea becoming a deep ocean, a desert becoming a floodplain, a tropical forest being buried under volcanic ash, and the fossils in sedimentary rock are the illustrations in this stone library. Trilobites in the Cambrian layers, 500 million years old. Ammonites in the Jurassic layers, 150 million years old. Mammal bones in the Cenozoic layers, tens of millions years old. The Grand Canyon, from rim to river, spans nearly 2 billion years of sedimentary history. The Dolomites in Italy, those stunning, pale-colored peaks in the northeastern Alps, they're made of dolomitic limestone, the remains of ancient coral reefs from the Triassic period, about 250 million years ago, when the area was a warm, shallow sea. The peaks of the Dolomites are literally ancient coral reefs, pushed kilometers into the sky by tectonic forces, standing now as some of the most dramatic mountain scenery on Earth. Coral reefs in the sky. It sounds impossible, but that's what they are. And then there's metamorphic rock, rock that has been transformed by heat and pressure, without melting entirely, into something new. The word comes from the Greek metamorphosis, a change of form. Take limestone, Subject it to enormous pressure and heat deep in the Earth's crust, and it becomes marble. Take shale, compress it, and it becomes slate. Take sandstone, squeeze it hard enough, and it becomes quartzite. Metamorphic rocks are common in the cores of mountain ranges, where the pressures and temperatures are highest. The Himalayan core contains zones of intensely metamorphosed rock, gneiss and schist and marble, that record the incredible forces involved in the continental collision. The patterns in metamorphic rock, swirling bands of light and dark minerals, folded and contorted like taffy, are a visual record of the stresses the rock endured during mountain building. Every fold, every stretched mineral grain, tells you about the direction and magnitude of the forces that were acting on it. And here's what ties all three rock types together into the mountain story. Mountains are not made of one type of rock. They're made of all three, mixed together, layered, folded, faulted, and juxtaposed in complex ways that record the mountain's entire history. A single mountain peak might have a core of igneous granite, flanked by metamorphic schist that formed when the granite's heat transformed the surrounding rock, topped by layers of sedimentary limestone that were once ocean floor, all of it tilted, folded, and cut by faults. Reading a mountain's geology is like reading a novel written in 3 different languages simultaneously. But once you learn the languages, the story is extraordinary. Let me give you a specific example, because specific is always more interesting than general. The Matterhorn, that iconic pyramidal peak on the Swiss-Italian border, one of the most recognizable mountains in the world. It rises 4,478 meters above sea level, and its sharp horn shape, as we talked about earlier, was carved by glaciers eroding from multiple directions. But the geology is what makes it really interesting. The summit of the Matterhorn is made of gneiss, a metamorphic rock that originally came from the African plate. Specifically, it's a piece of the Adriatic microplate, a fragment of the African continental crust. Below that, there's a band of oceanic crust, the remnants of the Tethys ocean floor, wedged between the African-derived rocks above and the European-derived rocks below. The Matterhorn is, geologically speaking, a piece of Africa sitting on top of a piece of ocean floor, sitting on top of Europe. The collision that created the Alps brought together rocks from different continents, different oceans, different eras, and stacked them up in a sequence that records millions of years of tectonic history in a single peak. If you could read every rock layer in the Matterhorn, you'd be reading the autobiography of an entire ocean that was born, lived, and died as 2 continents slowly closed the gap between them. Now, this kind of geological storytelling isn't just academically interesting. It has practical consequences. The type of rock a mountain is made of determines everything about how it behaves, how it erodes, how stable its slopes are, how it responds to earthquakes, whether it's a good place to build a road or a tunnel or a dam. Granite is hard, strong, and relatively stable. Limestone dissolves in slightly acidic water, creating caves and sinkholes. Shale is weak and prone to landslides. Metamorphic rocks can have complex internal structures, foliation planes, where the rock is weakest and most likely to fail. When engineers plan a tunnel through a mountain, the first thing they do is study the geology in detail, because the rock type determines everything about how the tunnel will be excavated, supported, and sealed. The Gotthard Base Tunnel we talked about earlier passed through a dozen different rock types over its 57-kilometer length, and each type required different excavation techniques, different support systems, different waterproofing approaches. The tunnel's engineering was, in a very real sense, a conversation with the mountain's geology. And speaking of practical consequences, there's another way that mountains matter to the modern world that doesn't get talked about enough. Mountains as water towers. Because a huge fraction of the world's freshwater supply comes from mountain snowpack and glaciers. In the western United States, for instance, mountain snowpack in the Sierra Nevada and the Rockies provides about 75% of the water supply for millions of people. The snow accumulates during the winter, sits on the mountain as a frozen reservoir, and then melts gradually during the spring and summer, feeding rivers and filling reservoirs at exactly the time when water demand is highest. It's a natural storage system that's been working for millennia, and it's a system that climate change is dismantling. Here's the problem. As temperatures rise, more precipitation falls as rain instead of snow. The snow that does fall melts earlier in the spring. The result is that the water comes down the mountain faster, in bigger, more concentrated pulses, instead of the slow, steady melt that the water infrastructure was designed for. You get more flooding in the spring and less water available in the late summer, when you need it most. The reservoirs fill too fast and then run dry. It's a fundamental mismatch between the timing of water supply and water demand, and it's getting worse year by year. And then there are the glaciers themselves, the long-term frozen reservoirs that feed some of the world's most important rivers. The glaciers of the Himalayas and the Hindu Kush feed the Ganges, the Indus, the Brahmaputra, the Yangtze, the Yellow River, rivers that provide water for over 1 billion people. These glaciers have been retreating for decades, and the rate of retreat is accelerating. A comprehensive study published in 2019 found that Himalayan glaciers lost ice twice as fast between 2000 and 2016 as they did between 1975 and 2000. In the short term, faster melting means more water in the rivers, which can actually cause flooding. In the long term, as the glaciers shrink and eventually disappear, the rivers will carry less water, particularly during the dry season, when glacier melt is the primary water source. The consequences for agriculture, for drinking water, for political stability in one of the most densely populated regions on Earth, they're enormous. This is one of those places where geology, climate science, engineering, and politics all collide. The mountains don't care about national borders. The Himalayas span China, India, Nepal, Bhutan, Pakistan, Afghanistan. The water that flows from those mountains is shared, fought over, negotiated. The Indus Waters Treaty of 1960, one of the most successful water-sharing agreements in history, divided the rivers flowing from the Himalayas between India and Pakistan. It's held for over 60 years, through wars and crises. But as the glaciers that feed those rivers shrink, the available water shrinks too, and agreements that worked when there was enough to share become much harder to sustain when there isn't. And this connects to something broader about mountains and climate that's worth understanding, because it goes beyond just water supply. Mountains are sentinels of climate change. They warm faster than the global average, a phenomenon called elevation-dependent warming, because of feedback mechanisms involving snow cover, water vapor, and surface albedo. What this means in practice is that mountain ecosystems are among the most sensitive to climate change on the planet. Tree lines are creeping upward. Alpine meadows are shrinking. Species that are adapted to cold, high-altitude conditions are being pushed higher and higher up the mountain, and eventually, they run out of mountain. They have nowhere left to go. It's called summit trap extinction, and it's already happening to some species of mountain pikas and alpine plants. But let me bring this back to something more immediate, something you might encounter if you ever go walking in the mountains yourself. Because one of the most profound things about mountains is what happens to your body when you go up into them. And this is where the physics of the atmosphere meets the biology of the human body, in ways that are genuinely fascinating, and at the extremes, genuinely dangerous. Here's the basic physics. The atmosphere is held to the Earth by gravity, and it's compressible, meaning the air near the surface is compressed by the weight of all the air above it. So as you go up, there's less air above you, which means less pressure, which means the air is thinner. At sea level, atmospheric pressure is about 1,013 millibars, what we call 1 atmosphere. At the summit of Everest, 8,849 meters up, the pressure is only about 330 millibars, roughly 1/3 of sea level. And here's the critical thing. The proportion of oxygen in the air is the same at any altitude. It's always about 20.9%. But because the overall air pressure is lower, there are fewer oxygen molecules in each breath you take. At the summit of Everest, each breath gives you roughly 1/3 as much oxygen as a breath at sea level. Your body needs to do 3 times as much breathing to get the same amount of oxygen. And your body can, to a remarkable degree, adapt. This process is called acclimatization, and it's one of the most elegant examples of physiological plasticity in human biology. When you go to altitude, your body starts making changes almost immediately. Your breathing rate increases. Your heart rate goes up. Over days and weeks, your body produces more red blood cells, increasing the oxygen-carrying capacity of your blood. The blood vessels in your lungs adjust to distribute blood flow more evenly. Your muscles become more efficient at extracting oxygen from the blood. Himalayan Sherpas and Tibetan Highlanders who have lived at altitude for generations show genetic adaptations to low oxygen, variations in the EPAS1 gene, sometimes called the super athlete gene, that help them function at altitudes that would incapacitate most lowlanders. But there are limits. Above about 5,000 meters, even with acclimatization, the human body starts to deteriorate. You can't sustain yourself indefinitely. You lose weight, you lose muscle mass, your cognitive function declines, your sleep is disrupted. And above about 8,000 meters, the so-called death zone, the oxygen level is so low that your body is actively dying. You're using up energy faster than you can take in oxygen to replenish it. Your body is literally consuming itself. Climbers who spend time in the death zone without supplemental oxygen describe a profound mental fog, an overwhelming exhaustion, a feeling that every step requires a conscious, desperate act of will. The death zone on Everest has claimed hundreds of lives, and many of the bodies are still up there, frozen in place, too difficult and dangerous to bring down. The story of climbing Everest is one of those mountain stories that deserves some space, because it's a story about human ambition, engineering, physiology, and hubris, all tangled together. The first confirmed ascent of Everest was on May 29, 1953, by Edmund Hillary of New Zealand and Tenzing Norgay, a Sherpa from Nepal. They were part of a British expedition led by Colonel John Hunt, and their summit push used supplemental oxygen, bottled oxygen that they carried in metal tanks on their backs. The equipment was heavy, bulky, and primitive by modern standards, but it made the difference between life and death at those altitudes. Hillary and Tenzing spent about 15 minutes on the summit. Hillary took a photograph of Tenzing holding his ice axe with flags attached. There's no photograph of Hillary on the summit, because Tenzing didn't know how to operate the camera. But here's something that often gets overlooked in the Everest story. Whether Hillary and Tenzing were actually the first to stand on top of Everest is one of the great unsolved mysteries of mountaineering. In 1924, 29 years before their ascent, 2 British climbers, George Mallory and Andrew Irvine, were last seen going strong, high on the northeast ridge of Everest, less than 300 vertical meters from the summit. They disappeared into the clouds and were never seen alive again. Mallory's body was found in 1999 at about 8,155 meters, frozen and remarkably well preserved. His snow goggles were in his pocket, suggesting he may have been descending in the dark after a summit attempt. But the camera he was carrying The camera that might contain photographs showing whether they reach the top has never been found. Irvine's body has never been found, though there have been recent expeditions specifically to search for it, and, hopefully, the camera. Did Mallory and Irvine reach the summit in 1924? We may never know. The climbing community is divided. What's remarkable is that they were attempting it with cotton clothing, hobnailed boots, and rudimentary oxygen equipment that leaked and malfunctioned constantly. The technological gap between their equipment and what modern climbers carry is almost hard to comprehend. Modern mountaineering gear, Gore-Tex shells, synthetic insulation, titanium ice axes, plastic double boots, lightweight supplemental oxygen systems, represents decades of materials science and engineering. The evolution of mountaineering equipment is its own engineering story, a story of iterative improvement driven by the most demanding test environment imaginable. But Everest has also become something else in the decades since Hillary and Tenzing's climb. It's become a commercial enterprise, and the commercialization of Everest has created its own set of problems. Every spring climbing season, hundreds of climbers attempt the summit, most of them guided clients paying $50,000 to $100,000 or more for the privilege. Long lines form on the summit ridge, climbers waiting in the death zone for their turn to stand on top. In 2019, a photograph showing a long queue of climbers snaking up the final ridge went viral, prompting debates about overcrowding, safety, and the environmental impact of so many people on the mountain. And the environmental impact is real. Decades of expeditions have left Everest littered with abandoned tents, oxygen bottles, human waste, and trash. The mountain has been called the world's highest garbage dump. Recent cleanup expeditions have removed tons of waste. But the problem persists as long as the commercial operations continue. Now, let's pull back from Everest and talk about mountains in a broader sense, about how we measure them, study them, and understand their ongoing behavior using modern technology. Because the science of studying mountains has been transformed in the last few decades by technologies that would have seemed like science fiction to the geologists of 100 years ago. Start with GPS, the Global Positioning System, which uses a constellation of satellites to determine positions on the Earth's surface with extraordinary precision, has revolutionized our understanding of mountain dynamics. We mentioned earlier that Everest is growing at about 4 millimeters per year. We know this because there are GPS receivers installed on and around the mountain, continuously recording their positions with millimeter-level accuracy. The same technology is used to monitor tectonic plate motions worldwide, to track the buildup of strain along faults before earthquakes, and to measure the slow, steady deformation of mountain ranges in real time. Before GPS, measuring mountain heights and movements required laborious surveying expeditions that could only produce snapshots, a height measurement from this year compared to one from decades earlier. Now we have continuous, real-time data flowing in from thousands of stations around the world. We can watch the Earth move. And then there's satellite remote sensing. Satellites carrying radar, LiDAR, and multispectral cameras can map the surface of the Earth in extraordinary detail, tracking changes over time with a precision that was unimaginable a generation ago. Satellite measurements of glacier extent and thickness have given us a global picture of how mountain ice is responding to climate change. The GRACE satellite mission, Gravity Recovery and Climate Experiment, actually measured changes in the Earth's gravitational field caused by the loss of ice from glaciers and ice sheets. When a glacier shrinks, the mass of ice decreases, and the local gravitational pull decreases with it by a tiny but measurable amount. So we're using gravity, the most fundamental force in the universe, to weigh the world's glaciers from space, and the numbers are sobering. The world's mountain glaciers have been losing roughly 300 billion tons of ice per year in recent decades, contributing measurably to sea level rise. There's also INSAR, Interferometric Synthetic Aperture Radar, which is one of those technologies that sounds like something from a spy thriller, but is actually a standard tool in modern geology. Here's how it works. A satellite passes over an area and sends radar pulses down to the surface. The radar bounces back, and the satellite records the return signal. Then, sometime later, days, weeks, months, the satellite passes over the same area again and sends another pulse. By comparing the two return signals, you can detect changes in the surface position as small as a few millimeters. This means you can create maps showing exactly how the ground is deforming over time, where a mountain slope is creeping slowly before a landslide, where a volcano is inflating as magma pushes up from below, where a fault is slowly accumulating strain before an earthquake. INSAR has been used to detect the precursory inflation of Mount St. Helens before its minor eruptions in the 2000s, to map the ground deformation from the 2015 Nepal earthquake, and to monitor landslide-prone slopes in the Alps and the Andes. We're essentially taking the pulse of mountains from orbit. Let me tell you about one more mountain measurement, because it's a question that seems like it should have a simple answer, but turns out to be surprisingly complicated. What is the tallest mountain on Earth? You're probably thinking Everest, and by the most common definition, height above sea level, you're right. Mount Everest stands 8,849 meters above mean sea level, as confirmed by a joint Chinese-Nepali survey in 2020. But above sea level is a more ambiguous concept than it sounds. Sea level isn't a fixed, universal reference point. The surface of the ocean is lumpy. It bulges outward at the equator because of the Earth's rotation, and it's affected by gravitational variations, ocean currents, and tides. The mean sea level that we use as the 0 point for elevation measurements is a mathematical construct, a theoretical surface called the geoid, which represents the shape the ocean would take if it covered the entire Earth and was affected only by gravity and rotation. Different countries use slightly different geoid models, which is part of why the height of Everest has been measured differently by different surveys over the years. And here's where it gets really interesting. If you measure from base to summit instead of from sea level, the tallest mountain isn't Everest at all. It's Mauna Kea in Hawaii. Mauna Kea's summit is only 4,207 meters above sea level, less than half the height of Everest. But its base sits on the ocean floor, about 6,000 meters below the surface. Measure from base to peak, and Mauna Kea is over 10,000 meters tall, significantly taller than Everest. Everest's base, on the other hand, sits on the already elevated Tibetan Plateau, so its base-to-peak height is only about 3,000 to 4,000 meters, depending on where you define the base. And if you define tallest as farthest from the center of the Earth, then neither Everest nor Mauna Kea wins. The winner is Chimborazo, a volcano in Ecuador, whose summit is about 6,384 kilometers from the Earth's center. Everest's summit is about 6,382 kilometers from the center. Chimborazo wins because it's very close to the equator, where the Earth's rotational bulge pushes the surface outward. Even though Chimborazo is only 6,263 meters above sea level, about 2.5 kilometers shorter than Everest, it's sitting on the widest part of the planet's equatorial bulge, which gives it that extra bit of reach. So the tallest mountain on Earth is Everest, Mauna Kea, or Chimborazo, depending entirely on how you define tallest. And I love that, because it's a reminder that even something as seemingly straightforward as measuring a mountain turns out to be a question about definitions, about what exactly we mean by the words we use. Nature doesn't care about our categories. It just does what it does, and we have to decide how to describe it. And here's one more technology that's worth mentioning, because it connects the ancient story of mountains to the very cutting edge of modern science. Seismology, the study of seismic waves, vibrations that travel through the earth, generated by earthquakes, volcanic eruptions, or artificial sources, has given us the ability to see inside the earth. Not literally see, obviously, but to build images of the Earth's interior, the way a medical CT scan builds images of the inside of the human body. By recording how seismic waves travel through different types of rock at different depths, seismologists can map the three-dimensional structure of the Earth beneath mountain ranges. And what they've found is remarkable. Under the Himalayas, you can image the Indian plate diving beneath the Tibetan plateau, like a plank being shoved under a carpet. Under the Alps, you can see the remnants of oceanic crust that was subducted during the closing of the Tethys Sea. Under the Yellowstone region, you can see the enormous body of partially molten rock, the magma chamber, that feeds the Yellowstone volcanic system. These images are ghostly, blurry compared to a medical scan, but they're real. They show us the roots of mountains, the hidden structures that support the peaks we see on the surface. And they remind us that a mountain is just the visible tip of a much larger geological structure that extends deep into the Earth's interior. Mountains have roots, just like teeth. The crust beneath a mountain range extends downward into the mantle, like the keel of a boat extending below the waterline. The taller the mountain, the deeper the root. This is isostasy again, the principle we've come back to several times tonight. The idea that the crust floats on the denser mantle below and the height of a mountain is balanced by the depth of its root. When George Airy and John Henry Pratt independently worked out the mathematics of isostasy in the 1850s, they couldn't see the roots directly. They inferred them from gravity measurements and mathematical reasoning. Now, 170 years later, seismology lets us actually image those roots, and they're exactly where the theory predicted they'd be. It's one of those satisfying moments in science where observation catches up with prediction and confirms that the elegant mathematical idea was right all along. But let me take you somewhere else now, somewhere we haven't been yet, somewhere that connects the story of mountains to a much bigger, much stranger question: mountains on other worlds. Because here's the thing, Earth isn't the only place with mountains, not by a long shot. Every rocky planet and moon in our solar system has them, and the mountains we see on other worlds tell us about the geology of those worlds in the same way that Earth's mountains tell us about Earth's geology. The shapes, the sizes, the distributions of extraterrestrial mountains are clues to what's happening, or what happened, deep inside those worlds. Mars has Olympus Mons, the largest known volcano in the solar system. It's a shield volcano, like the Hawaiian volcanoes, but on a completely different scale. The summit of Olympus Mons is about 21.9 kilometers above the surrounding plains, nearly 2.5 times the height of Everest above sea level. Its base is roughly 600 kilometers across, about the size of Arizona. Why is it so much bigger than anything on Earth? Partly because Mars has lower gravity, about 38% of Earth's, so the rock can support a taller structure before collapsing under its own weight. But more importantly, Mars doesn't appear to have plate tectonics. On Earth, tectonic plate motion carries the crust over volcanic hotspots, creating chains of volcanoes, rather than allowing one volcano to build up indefinitely. Hawaii, for instance, is a chain of volcanoes formed as the Pacific Plate moved over a stationary hotspot. On Mars, without plate motion, the Olympus Mons hotspot stayed in one place, and the volcano just kept growing and growing for hundreds of millions of years, possibly even over 1 billion years, piling lava higher and higher without the crust moving out from under it. Venus, on the other hand, has mountains that suggest a very different geological history. Maxwell Montes, the tallest mountain on Venus, rises about 11 kilometers above the mean surface level, roughly in the same range as Everest on Earth. Venus's surface is almost entirely volcanic, covered in basaltic lava flows. But the mechanisms of mountain building on Venus are still debated. Venus may have had plate tectonics in the past, or it may reshape its surface through periodic catastrophic resurfacing events. Essentially, the entire crust melts and resolidifies every few 100 million years. The evidence is ambiguous, and because Venus's surface is hidden beneath a thick atmosphere of carbon dioxide and sulfuric acid clouds, studying it requires radar imaging from orbit. The Magellan spacecraft mapped Venus's surface in the early 1990s using radar, and the data revealed a world of volcanic plains, rift valleys, and mountain ranges that hint at tectonic processes but don't quite match anything we see on Earth. And then there's the Moon, which has mountains too. The lunar highlands, plus the rims of enormous impact craters and the central peaks of those craters, which form when the ground rebounds upward after the impact of an asteroid or comet. The Moon's mountains weren't built by tectonics or volcanism. They were built by violence, by things smashing into the surface at tens of kilometers per second. The central peak of the crater Tycho rises about 2 kilometers above the crater floor. The rim of the South Pole Aitken Basin, one of the largest impact craters in the solar system, has peaks that rise over 8 kilometers above the basin floor. These are mountains made of destruction, and they've been standing essentially unchanged for billions of years because the Moon has no atmosphere, no water, no erosion, no wind to wear them down, no rain to wash them away. They're as close to permanent as anything in the solar system gets. And that contrast between the Moon's ancient, unchanging mountains and Earth's constantly churning, growing, eroding ones tells you something profound about what makes Earth special. Earth is a living planet, not just biologically alive, though that too, geologically alive. Its interior is hot, its mantle convects, its crust moves, its surface is constantly being reshaped by the interplay of internal heat and external forces. Wind, water, ice, life. Mountains on Earth are born, grow, and die. They're part of a cycle. The rock that erodes from a mountain is carried by rivers to the sea, deposited as sediment on the ocean floor, subducted back into the mantle at a convergent plate boundary, melted, and eventually recycled, rising again as magma that builds new mountains. The rock cycle, geologists call it. It's been running for over 4 billion years, and it's still going. The atoms that make up the mountain you hiked last summer might have been part of a different mountain 200 million years ago, and part of the ocean floor 100 million years before that. Everything is recycled. Nothing is wasted. The Earth is the ultimate recycling machine. And here's something I find quietly amazing. We live at an extraordinary time in the Earth's geological history to have mountains at all. Because mountain building requires active tectonics, and active tectonics requires a hot interior, and the Earth is slowly, gradually cooling. Eventually, and we're talking billions of years from now, the Earth's interior will cool enough that the mantle convection driving plate tectonics will slow and eventually stop. The plates will freeze in place, volcanic activity will cease, and without the internal forces that build mountains, erosion will gradually level the surface. The mountains will erode away, one grain at a time, and there will be nothing to replace them. The Earth will become, eventually, a smooth, flat, geologically dead world, like the Moon or Mars, worlds that may have had active geology once, but have long since cooled and quieted. But that's billions of years in the future. Right now, the Earth is magnificently, gloriously active. Plates are colliding. Volcanoes are erupting. Mountains are rising. And every mountain on the planet is both ancient and brand new. Ancient because the rocks it's made of may be billions of years old. New because the mountain itself, in its current form, is being reshaped every day by the slow work of wind and water and ice and gravity. Let me leave you with something, a thought to carry into sleep. There's a concept in Japanese aesthetics called mono no aware, an awareness of the impermanence of things, and a gentle sadness at their passing. It's the beauty of cherry blossoms, which are most beautiful because they fall. Mountains, for all their apparent solidity, are subject to the same impermanence. They just operate on a longer time scale. The Himalayas will be ground flat. Everest will be a hill. The Alps will be a gentle undulation. The Andes will be a memory, written in ancient sedimentary layers on some future ocean floor. Even the greatest mountains are temporary arrangements of rock, brief upwellings on the surface of a planet that is constantly, quietly, patiently rearranging itself. But temporary, on a geological timescale, means tens or hundreds of millions of years. And on a human timescale, mountains are the most permanent things we know. They were there before we were born. They'll be there long after we're gone. They're the closest thing to eternity that we can touch with our hands and see with our eyes. And there's something deeply comforting about that, about knowing that the mountains are out there right now, in the dark, under the stars, doing what they've always done, rising, eroding, rising again. Slowly, patiently, in no hurry at all. The forces that build mountains are the same forces that shape everything. Heat flowing from the inside of the earth outward, gravity pulling everything downward, water and ice sculpting the surface. These are simple forces, fundamental. They don't require intention or intelligence, just physics, just the laws of nature, operating over unimaginable stretches of time, producing landscapes of staggering beauty and complexity from nothing more than heat, gravity, and patience. And you know, there's a kind of mathematics to it that I find beautiful. The forces are simple, but the results are infinitely complex. A mountain range is a fractal. Its outlines are jagged and complex at every scale, from the shape of the range as a whole, to the shape of an individual peak, to the texture of a single rock face. The same forces of uplift and erosion that shape the overall form also shape every detail, every ridge, every gully, every scree slope. It's simplicity generating complexity, the same way simple rules in mathematics can generate patterns of infinite intricacy. The Earth doesn't need a designer. It just needs heat, gravity, water, and time. And what it produces over millions of years is something that rivals anything any mind has ever created. So as you drift off tonight, maybe picture this. Somewhere, right now, two tectonic plates are grinding past each other. The stress is building along a fault. In 100 years, or 1,000, or 10,000, there will be an earthquake, and a mountain somewhere will jump upward by a few centimeters. Somewhere else, a glacier is creeping down a valley, grinding the rock beneath it, carving a landscape that hikers will walk through thousands of years from now and wonder at the beauty. Somewhere, rain is falling on a peak, and a tiny grain of sand is being loosened and beginning a journey that will take it down a mountain, into a stream, into a river, into the ocean, onto the seafloor, and eventually, millions of years hence, back into the belly of the earth, where it will be melted and remade, and perhaps one day rise again as part of a new mountain, on a continent that doesn't yet exist, in a geography that no one alive today could possibly imagine. That's the mountain story. It has no ending, because it's still being written. The same processes that built the Himalayas 50 million years ago are building mountains right now. The same erosion that leveled the ancient Appalachians is carving the Rockies right now. The whole vast, slow, beautiful cycle continues, as it has for over 4 billion years, and as it will for billions more. Mountains rising, mountains falling, the earth endlessly reshaping itself, patient beyond anything we can truly comprehend. And you, here, tonight, lying still, breathing slowly, you're part of it. The calcium in your bones, the iron in your blood, the silicon in your cells, all of it was once rock. All of it was once part of the Earth's crust, part of a mountain perhaps, or part of the ocean floor that would one day become a mountain. You're made of mountain stuff. You're borrowed atoms, on loan from the planet for a few decades, and when you're done with them, they'll go back into the cycle, into the soil, into the rivers, into the rock. Maybe they'll be part of a mountain again someday, so let that thought settle. Let it be gentle. The mountains are out there, and they're not going anywhere, at least, not on any time scale you need to worry about tonight. They'll be there in the morning. They'll be there next year. They'll be there when your great-great-grandchildren are old, solid, patient, quietly rising and quietly eroding, doing what mountains do. And right now, the most important thing in the world is that you're warm and you're comfortable, and you can let all of these ideas, plates and magma and glaciers and fossils and rain shadows and isostasy, you can let all of them blur together and fade, like distant peaks disappearing into cloud. They'll still be there when you come back to them. Mountains are very, very good at waiting. Sleep well.